Welcome back to the final video in our series on image diffusion filtering. This video is more or less a wrap up of what we have seen so far. If you recall, in the last one we actually managed to implement a nonlinear filter, and now we're going at this last one we're going to discuss the final optimization that we can do when implementing like this filter, which is parallelization, and a trend that has been very popular lately, which is to run all of these codes in the GPU, right? So first we're gonna discuss some issues about that. So um, just going ahead and telling the conclusion, uh, GPU does speed up things a lot, but you do need some money, right? Because I will run the filter now in my laptop. It has an integrated graphics card, but it's because it's a mobile graphics card in a laptop. We're gonna see that it actually doesn't get any faster, and then since I don't really have like the hardware right now to test in a way that would optimize, I decided to put this topic in a way because it's important. But in any case, it's the knowledge of how you implement things in a graphics card is very powerful, and if you do manage to have the hardware or you're programming for software that is going to run in a high-end machine, all this will be very relevant. Okay, so first of all, what is the thing between GPU and CPU? There are several differences that we need to consider, right? So when and in the CPU, clock speeds are generally faster, right? So if you see the clock speed of any CPU processor, it's usually today they're more or less around 3 gigahertz, and in a graphics card, even in a high-end one, it will be around 2 gigahertz or 1 gigahertz or something. So you see that one core of the CPU is generally faster than a core in the GPU, right? The other thing is that the CPU has a feature called interrupts, which kind of allows the processor to pause execution and delegate execution to something else, and then this is essentially what gives a lot of the stuff that makes a modern programming language possible. For example, exceptions, reads input and output, and syscalls to allocate memory, and etc. And also, CPU can really keep more memory in cache. If you when you access RAM from the CPU, the amount of RAM that you can fit into the cache is greater than in the GPU. So it is not really that straightforward when a GPU will be faster than a CPU. That's what I mean to say by that. Now, if we go into the GPU side, we are usually now use OpenCL to program it, and then so how did OpenCL came about? In the beginning, GPUs came out because they needed to like perform some very dumb operations in thousands or sometimes millions of points, and these could all be parallelized very easily. And the GPUs were originally some hardware tailor-made to do that kind of operation pretty fast, like rotating a triangle, adding a color to it or whatever. But with time, there arose the need for for example, implementing lighting in a scene, or shadows, which is like also lighting. And sometimes you have a material and then you have to displace the points a little bit to create some texture. And all of these would be much faster than on this GPU, and then started to emerge the concept of a shader, which was like custom code that you run on the GPU. And well, with time, some researchers took notice, more or less people related to scientific computing took notice, and then they realized that they could like run numerical simulations on the GPU, right? And use the GPU to like solve weather equations or whatever. And initially this was like kind of a hack because the thing was made do to do geometric operations, but it worked. And then with time, OpenCL came about, which was like a language that you can like a general purpose language that you can run in the CPU that you want. But again, you should remember that in the GPU you have like lower clock speeds and is lower memory access. So the only way that the GPU can actually be faster than the CPU is if you can use it massively parallelization, right? So if, because for example in my machine the CPU has like 4 cores, right? And even in this dumb laptop that I have, its graphics card, its dedicated graphics card can have a work group of 128 uh, items, right? I don't think they are all of these are physical cores. There is some optimization going on. I don't know exactly how it works, but you can see that if you have like 128 and you compare with 4, so this is the only way that this GPU can eventually become faster than CPU code. So if you're going to put stuff in the GPU, you need to make it parallel, because or else it makes no sense. This is pretty much the idea of this talk, right? And also in OpenCL you have some called the local and the global dimension, and so the global is kind of unlimited for most applications, and the local one is limited by the hardware. So essentially when you're going to run an OpenCL kernel, what you need to do, you need to specify the global dimension, the local dimensions, and the global dimension is always a multiple of the local one, right? And the global is more or less the amount of tasks that you're going to run in an OpenCL kernel, and while the local one is something more tied to the hardware and it's more limited by the hardware. And the only reason that this distinction exists is that sometimes if you will need to synchronize threads, so they can run in parallel, but up to a point sometimes they need to wait for other threads to finish so that the output is not completely wrong. And the thing is that this synchronization can only work if the threads are in the local group. So for example, if you have 128 threads in a local group, and if you start a kernel with like 1024 global ones, if you want to synchronize stuff, you can only do within threads in this 128 group. And the reason for this is that this thing scales better in hardware. Right? This is like the only reason that this thing exists, because it is generally cheaper to make a hardware that cannot synchronize than a hardware that can synchronize with everything, right? And also, if you're going to access local memory, which is memory from the GPU which never interacts with the outside world, this is only possible within a local work group, and it's generally much more limited, not as large as a CPU cache. In my machine, for example, it is 32 kilobytes, not enough to restore what we need to do in the Lena image, for example, to process it. And because it has like no interrupt, no syscalls or whatever, you need to allocate all the needed memory before the program runs. So let me just then go through the code and show what I mean. So what we do here, so the first step that I did, I optimized the diffusion code that we wrote, and then you see that before we had like classes and all of the C++, but I got rid of all of it because OpenCL is more or less like C. OpenCL does not have classes, right? And then instead of using object-oriented programming, I used some C-style structs for initializing everything, and then all of it is here, right? And then if we, oh, and there's also some code to load the image. This uses classes because it is not really relevant to the algorithm, but well, everything is here. And then the heart of the code is more or less this loop apply. I'll say we read the image, we evaluate the transpose, set the field for the Newton solver, then solve, then evaluate the transpose, set the field and solve, and then we go through this several times, right? Well, and then, so like I said, if we want to put this in the graphics card, we need to find a way to parallelize all of this. And what is the entity that we can parallelize if we go, well, this should be obvious from the code, but we can also see it here, because if you see that we have our loop is always in the lines, right? You see we have one loop for each line of the image, right? And the most natural thing to do would then be, well, we have one thread handle each group of lines. That is what we do here, right? But there's a problem. If you recall what we did in the algorithm, what we actually do is we transpose these things, right? And then later, the next part of the algorithm will actually run here in these lines. So because of this, since each of these blue things is transposing each of these groups, right? Before each of these red steps starts, these blue ones, all of them need to finish. So it's not only like parallelizing and then dividing the work into all of these threads, because if you just do this, it's possible that this red iteration starts when one of these blue ones did not finish yet. And how do we solve this? We'll solve this with the concept that OpenCL has. It is called a barrier. Okay, so then what is a barrier? Well, a barrier is a very useful construct for parallelizing programs, for synchronizing threads. It is essentially, it's a point in the code that you go here, and then once a thread hits the barrier, it will hang until all of them hit it. And only when the last one hits, then all of these threads are released by the barrier, right? And then this is what we have to do. We do the blue ones, and then we put a barrier at the end of this transpose operation, and then once all of the threads finished, they all hit the barrier, and then they are allowed to go again. And this is essentially what we do when if we go to our OpenCL kernel, you see that it's the same thing. I'm passing all of these parameters here, and then you see this function barrier here. This is the function that I'm talking about. And here at the beginning you see some calculation, because in OpenCL we can get the ID of the thread that started the local size where it is running, And then this is just some computation to see which rows and which columns is this thread responsible for in our iteration. All right. And then, well, to call this, there is, well, I highly recommend that you look at up a tutorial on OpenCL if you want to do all this. But this is like just creating, getting the device, the platform, then it creates buffers, and then there are some dummy rights here for OpenCL to allocate the buffer, and then it builds, and then it wires all of the arguments, and then it runs. And then you see that, notice something important here, that when this is the entry point of the kernel, which is the OpenCL speak the for the main function. And then you see here that these global things, this is kind of like arrays that you allocate in C, for example, because in OpenCL we don't have an malloc function. You have to allocate these things before the execution. And then you see here that the only thing that needs to actually be global is the pixels one, because this is the only thing that we actually read from the host. All of the others, they could be local because they only exist within these programs. We never really interact with it. But the problem is that my GPU in this laptop is very crappy, and it's like if I just put local in these buffers, it would not locate because it simply does not have enough memory, right? Uh, and well, the other concept here is the local size, which is like the amount of, like I said, the local dimension of the size of the work group that you are running on the kernel. And then here, if you see, I put 128. The global is 128, which is the same as the local one. My graphics card can actually go to 256, but for some reason, when I run this with 256, it's lower than in 128. I don't know why. Maybe these 256 is some virtual stuff or whatever. But in any case, I can run. Let us see. So it is diffusion CL. I have to link OpenCL, and here it is CL, and we can just run this, and you see that it will actually run. Create the program build. And there we go. You see that it took 10 seconds. So this is in microseconds. So it took 10 seconds to run. After it built there, it takes some time to build the kernel before, and you will see that it is pretty much working like in the future. It ran in the GPU, right? And then, but like I said, this is actually a very crappy graphics card, while it is fast. So if I instead run, this is like the CPU code, single-threaded, and now I'm compiling with optimization, this O3 here. You see that I can do the same thing. But it only takes like 2.5 seconds, right? So yeah, it is very, very weird stuff. I think maybe if I added some colors, because when you put colors you have to add the other color channels, maybe the GPU would eventually catch up to the CPU code and we would see some more improvements. But with the graphics card that I have, it is what I can do. So it is like I said, sometimes the CPU can outperform the GPU because of all the other stuff that you need to take into consideration. But yeah, if you have a high-end GPU, please try it out. It should outperform. I don't have the limitations that I had here. But anyway, that's the course. We actually managed to implement a filter with a very efficient algorithm which can be parallelized well when running the GPU. It was a lot of fun doing this course. There were some issues in the production, like sometimes my microphone was not working well. Sometimes there were errors in the notes, and maybe in the future we'll like redo this series without the experience that I had in like in a more professional way. But anyway, I think I actually reached the goals that I had when I started this series out. And if you watched through the end, thanks a lot. And if this was useful to you, please like the video and subscribe to the channel. And bye bye.